Thank you very much for this kind introduction. Maybe what's more pertinent to this talk is the fact that I did work in industry while doing my PhD, and even after my PhD for a few years. If you are a young person here pondering whether to do a PhD while working full-time, it's not a good idea, but we can discuss that during break. However, I do have an industrial background as well as Ralph, but I made the switch to academia even earlier, and that's, again, subject of another, maybe over dinner talk. Today, I'm going to try to tell you a few words about how we use AutoML, not only in healthcare, but healthcare will be the anchoring example, and how do we go between requirements, solutions, software, and what we have learned when we implemented this in large-scale systems. So, over the last 20 years, together with a generation of brilliant students, since I moved to academia, we did work on many different fields. We started in networking and multimedia. We did work on smart grids, actually, transportation systems, smart cities, finance, economics, and most recently, in the last decade, medicine and education. The reason I'm telling you all that is really what I'm going to talk about today, while anchored in medicine and healthcare, is really not only about healthcare and medicine. I think the same ideas would transport with different incarnations to all these fields. So let us think about an augmented clinician, but in your case, you can think about an augmented engineer or city planner or finance person. And the idea is, of course, to provide actionable intelligence with the help of machine learning. And in medicine, one of the simplest things we want to do is to provide risk scores to the clinician, or if he's a clinical researcher, hypothesis. So the trouble with this, you all know, I guess, if you are familiar with machine learning, is that different methods may be best in different settings and for different data sets. So what you see here is one of the early examples from our lab of around 7 years ago, when we tried different machine learning methods for different types of data sets. They were all cardiovascular disease data sets, so they were related data sets. And yet, different machine learning models were having different performances for different data sets. What's also interesting here is that the performance with respect to a Cox regression was very different or very similar. And what you also see there in medicine, but not only in medicine, we also have human-crafted scores. And you would say, why do we need human-crafted scores? Well, as a clinician, often would tell me, I'd like to do this in my head. 3 points because this person is obese, 2 points because she's a woman. And this is how they calculate scores in their heads. And that has some advantage, of course. So what you see here is different data sets for the same purpose, more or less, different models working differently well for them. So this is problem number one. So for somebody that doesn't have expertise in machine learning with a field that's operating at this space of innovation, what model to choose? If you choose a machine learning model, there may be also millions of hyperparameters you may need to optimize. And that requires expertise in machine learning. Problem doesn't stop there, because often you may want to ensemble different methods together to achieve even better performance. That complicates the issue. Also, not everybody cares about area under receiver operating curve. Very often we may care about some other metrics. We may care about precision recall. We may care about trustworthiness or other metrics of performance, and then the methods may differ in terms of their performance. And also, if you have shifts and drifts in data, and we usually do, the performance will change again. So all is a mess, of course. And this is what brought me to AutoML back in 2017, the fact that we really wanted to do this at scale. Another thing that brought me to it, and discussing this morning with Frank, it seems that he had a similar experience, but in another field. I also became very soon, as soon as I started to do machine learning for healthcare, I was at the time in the United States, and everybody in my university at UCLA wanted to have another risk score built. So after building the first 10 of them, I started to get bored to build yet another one. So I thought, well, how can I automate myself? And this is how our own work on AutoML started. Of course, we also need explanations associated with these predictions in the case of medicine, but that's a totally different subject I'm not going to talk about here. So we wrote kind of a big manifesto on how AutoML can empower ecosystems like the healthcare system, but again, this transcends medicine. And the reason we liked it is because it can define and solve problems systematically. So we no longer have this situation which we often see in machine learning community. Everybody is defining their niche problem in a very special way with a specific data set, and we can't even compare against each other. If it is to talk about a systematic solution in industry, we need systematic ways of formalizing it. We need clear methods and clear benchmarks to improve among each other, and AutoML is a good framework to do that. We also, and I'm going to talk more about that a little later, we need to build, validate, and confirm solutions before we implement them, especially in a system like healthcare or smart cities or even finance. What's good about AutoML also, it allows communities to come together, and very successful work, of course, of AutoVeca has shown the way in that regard. We really need to build our joint collective intelligence together in AutoML community. This has been done very successfully. And finally, we want to do that to empower people outside the machine learning community to use the best possible tools the community has at scale. So, as I mentioned, our own journey in this case started with a method that we call autoprognosis, which was aimed at building clinical risk scores at scale for many diseases. And because medical data has a lot of missing data, has a lot of features, and we need to calibrate to the population of interest, we need to build not only methods for prediction, but also entire pipelines that allow for, again, imputation, feature selection, classification, and calibration. We also need to learn from other data sets, and we need explanations, but I will not focus on that. Now, what was the challenge that we overcome back in 2018 is really the fact that we have these many possible pipelines. So it's no longer just a question of choosing the machine learning model or the parameters associated with it, but this may change depending on what comes before, which may be an imputation method that may allow a particular prediction method to be best, or the calibration that follows. So it's the interaction between these different steps of the pipeline that makes the problem even more challenging and an important issue in medicine. So what we did at the time, again, long ago, I'm not going to go into that, we came up with this idea of sparse additive Bayesian optimization such that we can learn very efficiently when we have this huge number of dimensions and interactions between the pipelines. Since then, this is long ago by now, a variety of risk scores have been built in medicine with this tool. You see here just a few of them, but there are many others. And this is wonderful, but there are some lessons learned. So before I go to the lessons learned, let me say that because we had this AutoML tool, we were really the first in the UK, academic or industrial, to join forces with NHS early in the pandemic to build a risk score, not for patients, whether they die from COVID or not. Funny enough, that was not something of interest. What was the most important and most urgent task for NHS, which was very overwhelmed by the pandemic, was to predict who needs resources, especially hospital beds in the ICU and ventilators. So we predict the risk of congestion, if you like. And it was very easy for us to repurpose autoprognosis to do this task. So very early on, we repurposed it, and we start together with the NHS to run this at scale within the NHS system. But we were a little academic lab. Only 3 of my students volunteered to go on this journey, not even all my students. And we were interacting with NHS. So this is the moment in which we started to use a lot, to learn a lot. And this talk is mainly about that. So one of the things we learned is that we need to have ways to do rapid validation. The second is that we need to build demonstrators. And the third is that implementation is key. Let us talk about this. So we really noticed that it's not only about AutoML, it's also how do we build this to validate fast whether the methods work and demonstrate its use to stakeholders who don't care about AutoML or machine learning, they care about solving a specific problem. And one of the things that we learned will come a little later, which was that a lot of information was very difficult to acquire in a timely manner. So we really needed to determine the minimum amount of information we wanted. The lessons learned were manifold, and that led to AutoPrognosis 2.0, which is an endeavor where I joined forces with my postdoc Fergus, an engineer, Bogdan, who really actually helped us build a very robust software. Our original software was not robust. The second one that we have now is very robust. And a clinician, because we realized that while we think we understand the world of medicine, we really need a clinician to know what to build in that. And the reason this is at another level than the original version is not only that it's robust and it's also easy to use, it's easy to add additional methods, we open sourced it, and we have a huge amount of interpretability methods plugged into it. So that was very important. We also have very robust uncertainty quantification methods. So we have conformal prediction implemented as part of it, such that we know which predictions can be trusted and which ones cannot. And maybe the most important feature of AutoPrognosis 2.0 is that we can build demonstrators immediately. So if somebody doesn't have this skill, it can be done very fast. So AutoPrognosis 2.0 will build a user interface for you, thereby lowering the threshold in programming. And you can play with it if you like. What I want to show to you is how we use this AutoML tool for discovery, because I think that that's a lesson that we learned. And especially I'm going to ponder on the value of information. So two things we can do with AutoML. One is discover what information is valuable and what it is not for your prediction of interest. And number two is, do we need sophisticated AutoML machine learning methods, or can AutoML just provide to you a guarantee or information that your linear regression works very well, or maybe even your human-made risk score is good enough for this problem? So to illustrate this, I'm going to use UK Biobank, which is a very big data set, which contains many different types of risk scores that were collected for patients, for actually healthy people in the UK. And then there is a lot of follow-up. And what's interesting about this, we try to build cardiovascular risk scores on the basis of this data. Cardiovascular being a risk that's the highest in the UK of mortality, but that's kind of, in many countries, the biggest risk of mortality for both men and women. And what we wanted to ask is, can we improve risk predictions and can we discover new risk scores? This is in an older paper called AutoPrognosis, in which we use AutoPrognosis to do this. And what do we really try to do here? We try to compare this against both traditional risk factors. So these are risk factors which the experts knew were important for cardiovascular disease. And there are two risk scores usually used, either one that's built by hand, the Framingham score. The other ones are based on the traditional risk factors and use a Cox proportional hazard model, so a statistical model. This is with respect to the risk factors and the value of information. The second one, we wanted to look at if I give 400, all the different variables, will I still have performance improvement if I compare Cox against the best AutoML method? So what we want to determine is, on one hand, the modeling gain, how much performance improvement I have due to machine learning, and, for instance, how much the Cox proportional hazard model is going to be worse as opposed to the best AutoML framework that will potentially even select Cox or combination of Cox and other models. So this is what I'm going to call the modeling gain. And the other one is the information gain, where I'm going to say, let's fix the best machine learning model, and as selected by autoprognosis, and see how much performance improvement we have if we add on top of this well-known 7 variables that are important for cardiovascular disease, additional variables. How much gain we have. So first, the information gain was a very interesting one because we discovered different variables being important for different subgroups of people. For instance, for women, we discovered very different risk factors than the ones that were originally known. And that was very interesting and hypothesis generating. Also, what we learned was that many variables that were easy to measure, even a person could do it themselves, speed of walking, self-reported health, were very important variables. What about the modeling gain? The modeling gain initially looked kind of limited. So if you look at the average performance of, for instance, autoprognosis and Cox, there was improvement, but the improvement was in the order of 10% or less. And this was interesting to us. But then when we went one step further, we said, well, can we look at subpopulations of interest and see if additional performance improvement can be gained? This is when we saw a huge performance improvement between patients that have diabetes, for which we apply a model like a Cox proportional hazard model, as opposed to an AutoML framework like autoprognosis. So what lesson has been learned here is that while for the general population there may be no gain associated with nonlinear interactions, so Cox is already doing quite well, for a particular subpopulation of interest, diabetic patients, the improvement is huge. So one needs to look at these interactions not only at the population level, but also subpopulation level. Okay, now let me go one step further and ask another question which we have recently asked, and it appeared also during COVID. What's the minimum information I need to achieve a certain level of predictive performance? Often we think about information being costless because we have data sets, so we don't worry as a machine learning community where this information comes from. But we should worry because the reality is these data sets don't fall from the sky, and we need to acquire this information at pace, at runtime. So to illustrate this point, I want to show to you an example from lung cancer screening in the UK, where the survival is poor because cancer is diagnosed late. And if we could screen well, we can reduce by 20% these deaths. Why currently such a big problem to deal with this issue is because people measure 19 different things to determine whether somebody should be screened or not. 19 risk factors. This is much too much, and most clinicians, when they see a patient, don't bother. So what we wanted to do is, can we use an AutoML tool like Autoprognosis 2.0 to determine what's the minimum number of features we want to measure to achieve the same performance as a Cox regression with 19 variables. And what we show in this paper is that 3 variables are enough. So usually you think about machine learning, you need a lot of variables for machine learning to pay off. No, here quite the opposite is true. We have the same performance as Cox proportional hazard model with 19 variables if you use just 3 variables and AutoML. So it's really quite interesting to look at the value of information in this way, and this can be a game changer in lung cancer screening. Final thing I want to say, is it robust to translation to other countries and other settings? What we have tried to do in recent times was to see if we can use the current risk score both in the UK as well as in the US for breast cancer and do better with AutoML than regressions. And this risk score is used for making decisions on treatments. And what we did is we trained it on a subset of population in the UK data set we validated in the UK in an unseen population, and then without any retraining, we applied it to the US cohort. And again, we did autoprognosis, and what you see here is that this framework does better than the current risk score both used in the UK and US, predict, as well as a Cox proportional hazard model. It does better both in the population that it was trained, and does significantly better in terms of generalization in the United States data set. And also in subgroups. Again, this power of looking differently at different subgroups. You can do AutoML in medicine not only for predictions, but also for survival models, causality, temporal models, and imputation, and I'll talk more about that tomorrow during the keynote. And if you want to read about some of this work, please take a look at our website. And finally, I'd like to say that, again, AutoML can offer a lot for industry, I think, both in terms of easy deployment and open source packages, but also to build risk scores, to assess the value of information, which is a very important tool for that, to determine, do you really need as much information, or can we do with a subset? To provide uncertainty quantification associated with it, and improved uncertainty quantification as opposed to using just one model. And finally, enable us to do continuous learning as new variables and the data has shifts and drifts. So with this in mind, I'm ready to take questions. Thank you.
Two quick notes before we take questions. The first is that I would like to invite our online participants to ask any questions in the Zoom chat, and they can be relayed to the speaker here. And also, I would like to ask the speakers to please repeat any questions before answering them, again, to aid our online participants in understanding.
Thomas, is the mic not routed to online?
I
heard the microphone, that should be online as well.
I heard the catch microphone was somewhat muffled on the Zoom.
So if the catch microphone could be stronger on Zoom, then we don't need to repeat questions. Thank you.
There's a question over here. Let's get the microphone. Over here. Oh!
Thank you very much. Is it turned on?
There we go.
Thank you very much for the talk. I wondered if privacy would be another concern for these automated machine learning solutions. Like, the data is very sensitive, and if you have a feature that's very rare, it could potentially reveal some patients. So I wonder what could be done to make sure that the user doesn't reveal the data.
Thank you so much. This is a brilliant idea, actually, because indeed, the value of information is not only about acquiring features in terms of cost. There could be cost in terms of harm to the patient, because I need maybe to do a test, like an invasive test, or it could be a privacy harm. So indeed, one could use this exploration of what variables matter for different types of models through the AutoML framework by selecting the subset that is indeed private or not. So you are right, that's actually, I think, a great idea. I didn't even thought about that, but I think it's a great idea.
Thank you.
Time for perhaps one more question. Down here.
Yeah, wonderful. Thank you very much for the talk. You talked about the value of information. I was wondering, I mean, the kind of the VC dimension or the modeling power of Cox proportional hazards model is like rather limited, I would say. Do you pay a price in terms of the number of data, like for maybe using this more complex models, but getting away with less variables then? So basically, do you need more data than to fit these more complex models?
This is another very good question, whether we need more data. Possibly, definitely, I would say. So you may need more data in the sense that not more features, but maybe more patients, more data points. That's number one. However, as we all know, self-supervised learning is a way to potentially circumvent that. So you may not necessarily have only data that is labeled. You could have unlabeled data, and we have shown quite a lot of success with tabular data through self-supervision, where maybe you can train these models through additional data that's not labeled. So that may be a way to circumvent that.
Thank you very much.
Thank you.
Okay, thank you, Mihaela. And now